this kind of spectrum, the absorption line spectrum, is made when this gas absorbs some of the wavelengths out of a beam of light. But that's not super helpful all the time for a lot of clouds of gas. Because here's the thing, where are the clouds of gas that we're studying in astronomy? Where are these clouds of gas? Where are they? Don't overthink it. Are they in this room so that I could put a light bulb behind them? No. They're in space. So can I go behind the cloud of mystery gas and set up a light bulb if the mystery gas is in space? No. So we can't set this up in space most of the time. If we're lucky, a star will go behind the cloud of gas we're looking at, and we can try to use the star as the close to perfect light source and get an absorption spectrum off of it. But that doesn't always happen. So what do we do when the mystery cloud is just by itself? Well, chances are every gas that we're looking at in space has stars nearby. So those gases out there have absorbed light from nearby stars. But let me go back to my picture of an atom. When an electron pops up, does it want to stay up? Does the electron want to stay up when it goes up? No. It wants to come back down, right? It wants to come back down. And here's the kicker. If it took in light to pop up, when that electron falls back down, what happens? Let me ask that. That's the next question. If the electron took in light to pop up, what's going to happen when that electron pops back down? Don't overthink it. If light came in to pop it up, that means there's stored energy in here. Yeah, when those electrons fall back down, which is what they want to do, any light they stole to pop up, they're going to give right back off to pop back down, okay? So that means this. Check this out. Let me go back to that book picture. If we have this perfect light on this gas is getting pumped up by stealing light. There's the stolen wavelengths, right? But let's say we turned this light off. Let's say we turned it off. Now the gas cloud isn't stealing light anymore, and it doesn't want to have its electrons up. So the light it stole, it's like, you know what? I didn't even want this. I didn't even want this stuff I stole. So it lets its electrons fall back down, and any any light that got stuck in here will then come out. But, here we go. But, if we look at the light that comes out of this gas, let me block this light with my head. Once we've turned this light off, will every wavelength come out of this gas? Will we expect, when we see the light coming out of this gas, will this gas give off all wavelengths? Yes or no? Will it give off all possible wavelengths? No. It's only going to give off what it stole. So even if there isn't a light behind the gas, it's always going to steal light from nearby light sources. But it doesn't want to hold on to them. So if you look at just the gas without the light, then you're going to see it giving off its stolen goods, right? So in other words, if we turn this light off, how would we expect this picture to change over here? Well, the rainbow colors right here, those were coming from the light. So when we turn that light off, all of those will go dark. But because the gas wants to give off what it stole, it will give off the colors that were missing. So what will happen to this rainbow? What would this rainbow look like if we switch the situation? It'll go from this to this. So when the light's on, you see what the gas stole. But when you turn that light off, you only see the stolen goods. Does that make sense? So most of the rainbow is missing because we turned off that light. So this gas, just by itself, will only give off the things it stole from nearby lights. Okay? And so this kind of spectrum looks totally different from the other kinds of spectrum. And when we turn it into a graph, see how we don't really have that hill anymore? We just have these sticks. This kind of spectrum is called an emission line spectrum because now we're seeing what the gas emits instead of what it absorbs. So let me just go through those real quick. If you've got an absolutely perfect light source, it's going to make a continuous spectrum, which is a perfectly smooth graph. Continuous spectrum. If you put a gas in the way, it will absorb some of the wavelengths, and so you've got a rainbow with a few colors missing, or a perfect curve graph with a few colors missing. That's the absorption line spectrum. But if you then get rid of the light source and just look at the gas, it will give off its stolen goods and give you an emission line spectrum, which is mostly dark with just a few colors. Okay? And again, we can tell what this gas is made out of by the pattern we see over here. Because the same gas that absorbs this pattern basically makes just the inverted pattern when it's giving it off. So either one of those, the absorption or emission spectrum, can both tell us what something is made out of. Okay, let me give you guys some examples, just a couple of questions, and this is all we're going to talk about today. So here we go. Let's finish it up. So what kind of spectrum is this? What kind of spectrum is this right here? Is this a continuous spectrum, absorption, or emission? Give me one of those three. This is emission, okay? How about this one? What's this one right here? Is this continuous, absorption, or emission? Absorption. So you should be able to identify what kind of spectrum you're looking at. And again, this right here, I actually showed a second ago. I said that was the absorption spectrum of hydrogen. So can anybody tell me what element this is the emission spectrum of? This is the absorption spectrum of hydrogen. What element makes this emission spectrum? Hydrogen. And how can you tell? How can you tell that this is also hydrogen? Because the pattern is the same, right? Just inverted. Because the pattern is the same, just inverted.